Okay, here we are, lesson 1.3. We are going to be solving equations with variables on both sides. So let's take a look at what that's going to look like. Wow, lots of words here. So what are we going to learn? Solving the linear equations that have variables on both sides, and then to identify some special solutions and then apply it to some real life problems. So when we want to do this, when we want to solve these equations, they're going to have variables on both sides. The core concept says to solve an equation with variables on both sides, simplify one or both sides of the equation if necessary, then use inverse operations to collect the variable terms on one side of the equation and collect the constant terms on the other side to isolate the variable. Okay, so in your note-taking packet on our journal, student journal, on page 15, at the very top of the page, you have the steps. So we want to look first at both sides of the equation and make sure that they're both simplified, meaning do we need to apply the distributive property to remove any grouping symbols? Can we simplify by maybe collecting or adding together some like terms, right? Are there any constants that need to be added together or variable terms that need to be added together? Then step 3, collect variable terms to one side and constants to the other. Then isolate the variable using the inverse operation. And then of course step 5, your favorite of all, check your solution. So the cool thing about equations is you always have that opportunity to check your solution. So let's take a look. Here we go. So exercise 1 of the extra practice. We see that we have 12 minus 3x is equal to negative 6x, okay? So when we're talking about two sides of the equation, right here, I like to put a line down that equal side just to kind of like make sure we're not repeating some of the work on the same side. So we see a term of x on the left and a term of x on the right. Now we can't just simply add the like terms together because they're crossing over that equal sign, so we have to use inverse operations to move them. And I'm going to start by moving the 3x. So the inverse, you have 12 minus this 3x. If I add 3x to both sides, okay, notice on the left, negative 3x plus 3x, we get 0. So we have a 12. And then we have an integer problem here, negative 6x plus 3x. They're like terms, so we can combine them now like this. So negative 6 plus 3 will simply be 3x. Sorry, negative 6 plus 3 would be negative 3x. Got to get this straight. Okay, Miss Kleiman, let's go. All right, so 12 is equal to negative 3x. And we'll undo this multiplication on the right. That's where the variable is. So we want to divide both sides by a negative 3. Let me see if I can get that to right all the way. Divide both sides by a negative 3. So negative 3 divided by negative 3 on the right is like a 1. 12 divided by negative 3 is negative 4. So negative 4 is equal to x. And then you want to substitute it back into the original problem to check your work. And I'm going to save you time in your video by not doing that step. But for your accuracy, please take the time to do it. Okay, even if you're just using mental math. Number 2, notice we have on the left, we have 7 minus 5z, and on the right, we have 17 plus 5z. So it doesn't really matter, like on number 1, notice how the reason I added the 3x and moved it to the right is because there were no other terms with that 6x. But now that on number 2, when we have variables and constants on both, you'll start to find ways to make your life easier, whatever makes sense to you. Some people like to collect the variables on the left all the time. Some people will like to do the math so that you have no negatives if you can avoid them. I'm more of a put the variables on the left kind of person. So that means I'm going to go over here to the right in the 17 plus 5z, and I want to move this 5z, or I'm going to use the inverse operation so that that becomes 0. And so 5z minus 5z, and if I'm subtracting 5z, I have to subtract on both sides. Okay? But you could try it out if you wanted to and move this other 5z from the left to the right, which would be adding 5z to both sides. So you figure out which one you're most comfortable with, okay? But I'm going, this way with it. So with my variable. So on the right, I can simplify here, and I have 7. I have a negative 5z plus a negative 5z or a negative 10z. And that's going to be equal to the 17. Now I am limited, since I moved the variable to the left, I have to move the constant to the right, meaning I have to, now that all the z's are on the same side, I'm going to subtract 7 from both sides. Okay, 7 minus 7 is 0, always double check that, and then I'm left with a negative 10z. So there's a lot of detail work involved with keeping track of all the negatives. 17 minus 7 is 10. So when I divide both sides by this negative 10, as my last and final step, I will get z equal to a negative 1. And if you take the time to check your solution, you will find that that is correct, and it does satisfy the original equation. Moving on, you will have to turn the page to page 16 to find the problem for number 9. I've chosen to do number 9 because now we're kind of getting into that simplifying, right? We have some distributed property, possibly some like terms. So again, I like to kind of draw the line, okay? So I know which two sides of the equation I'm working on, and I am distributing a positive 8 inside the parentheses. So 8 times 2r is 16r. 8 times a negative 3 is negative 24. And then I simply finish with the negative r, and equal to, now I'm going to distribute this 3, so I'll have 9r plus 6. Okay? All right. Now, looking at the left, I still can simplify more because now I have some like terms, my 16r and my negative r. So I'll take 16r plus negative r, and I'll get a positive 15r. Minus 24 is equal to 9r plus 6. Again, I like to move my variables to the left, so I'll take and subtract 9r from both sides, from the like term only, right? So 9r minus 9r is 0. 15 minus 9r is 6r. Now I'm left with adding 24 to both sides because I want to move the constant to the right. Oops, 24. So I'll get 6r is equal to, and when I add 6 and 24, I get 30. So I'm finally going to divide both sides by 6, and I find that r is equal to 5. Through checking my work, I know that this is true. I just want to make sure that that looks like a 5 and not a 6. Okay, double check. Yep, that's a 5. Make sure. All right, on number 10. Whew, lots of things going on. So again, I'm going to start by drawing this line so I can keep track of what's happening on both sides because I have a lot of simplification to happen. When I see that I have 3x minus this 8 and then the parentheses, and I want to clear the parentheses, I circle that negative 8 so that I know that I'm multiplying or distributing a negative number. So then I have 3x, negative 8 times 2x is going to be negative 16x, negative 8 and positive 3 is going to be a negative 24. Moving over onto the right-hand side, I'm distributing a negative 6 to both numbers. So negative 12x, and negative 6 times 5 is negative 30. Okay. I still have more to simplify on the right, so I want to combine like terms. The two x terms can be combined. So 3 plus negative 16 is negative 13x minus 24. And I'm still have the same things on the right-hand side. So I would move the variable terms to the left and the constant terms to the right. So I'm adding 12x to both x terms. Then you can kind of also, if you wanted to, say, well, if I need to get rid of this constant, I'm treating those separately. But what if I added the 24 to both sides right here in this same step. It might save an extra line of work, but if that seems too jumbled for you, then don't do it, because then you want to check, this variable term crosses out here, but this constant term crosses out here. So negative 13x plus 12x is going to become like a negative 1x, right? The difference, negative 13 and a positive 12, when you find the difference, it's 1 and it's a negative 1. So negative x, since I've already gotten rid of the constant and I've moved the constant to the right by that step that I showed you with the red just to save space, the negative 30 and the positive 24 simplify to a negative 6, but I'm not done because negative x is not the variable isolated. We have to have it as a positive x. So I'll divide both sides by negative 1, and I'll get x is equal to a positive 6. And then make sure, if you're going to check it, go back to the original equation to check it. Okay, here we go. I know these take a lot of steps. Sometimes we'll have special solutions of linear equations. So, we just did 4 examples where they had one solution, but an equation that is true for all values of the variable, they call that an identity, and it has infinitely many solutions. And an equation that is not true for any value of the variable has no solution. So let's take a look at a couple of these special cases. All right. So, in number 11, and it's on page 16 in the student journal, we'll start by distributing, okay? And we have to distribute on both sides. So on the left, we're distributing a 6, and on the right, we're distributing an 8. So 6 times 4s is 24s, and 6 times 12 is 72. On the right, 8 times 3s is 24s, and 8 times a negative 14 is a negative 112. Okay, so Mrs. Kleiman likes to move her variables to the left. Let's start with this 24s. We'll subtract it. That's the additive inverse, and I know it goes to 0. I'll subtract it from the like term. But guess what happens in this case? 24s minus 24s is also 0. So in the bringing down the constants, right, I've got 72 is equal to a negative 112. But since I've kind of already eliminated the variables on each side, there's no need to move the constants. If I did, and I subtracted 72 and moved them to the right, I would have 0 is equal to, like, what, negative 184? And that's not true, but neither is 72 equal to negative 112. So because this is not true, right? We can say this is not true, so we would write no solution. So you don't have to write all the words, this is not true. I just did it for your notes so that you could know why we said that this is no solution. Okay? On the right over here, I'm going to change colors because I can. And I'm going to draw my line. Now on the left, we have 16f plus 24. Nothing changed there. But on the right, we have to do the distributive property. 16f plus 24. And at this point, this is where we call it the identity, right? Because it's the exact same thing. 16f plus 24 and 16f plus 24. Hopefully this is enough work for you to say, look, I don't have to do any more, right? If you just started problem solving because that became not apparent, you would also notice that these cancel, and 24 is equal to 24. And so, because this is true, it will be true for all values of x, or f in this case. So we would write infinitely many solutions. Okay? And so then sometimes, so pay attention to the directions, because there will be times in the homework where you're just solving them like we did in the first 4 examples of the video. And then there's going to be some where it's going to be asking you if it has, you know, one solution, no solution, or infinitely many. Okay? So if you can solve it like we did in the previous 4 examples, then you would say one solution. All right. One more example. The application to real life. So this problem we have the value of a surface area of a rectangular prism equal to the value of the volume. We want to write and solve an equation. First, we kind of sort of need to know, how do you calculate surface area? So the surface area of a prism is 2, it's adding up all the areas, okay? And there are 6 faces. So we have 2 with an area length times width. We have 2 with an area length times height, and we have 2 with an area width times height, and that's how we get all 6. For the volume, it is simply like area of the base times the height, and in this case that would be length times width times height. So for this problem, we have, it says that the value is equal to, the value of the surface area is equal to the value of the volume. So we have our formulas set equal to each other. Okay, is equal to length, width, height. And lucky for us, they gave us a picture. So we know what the length, what the width, and what the height is supposed to be, and we can substitute those values in for the L's, the W's, the H's, and then simplify. So remember in this first expression, 2 times L times W. So we would have 2 times X times 6 plus 2 times X times 6 again plus 2 times 6 times 6 equal to X times, and notice sometimes we use parentheses to show multiplication. The W is 6 and the H is 6. So this next step is to simplify. So 2 times X times 6 is 12X plus 12X plus 2 times 36 is 72. And X times 6 is 36X. So again, one more step to simplify. 24X plus 72 is equal to 36X. So this is kind of like one of those first examples where we want to subtract the 24X because there's X by itself on this side. So once we move the variable terms, we don't have to move the constant. Okay? So it's one less step to do. So we'll have 72 is equal to, and then 36 minus the 24 would be 12X. So divide both sides by 12. And we'll get 6 is equal to X. And that's what we wanted to find, the value of X. So there you go. If you wanted to plug it in, right, you could see that if you went back in and substituted it and found the volume, and then also substituted it and found the surface area, that those two values would be equal to each other. The only difference would be their unit label. Okay, this concludes the notes on lesson 1.3.